So in this presentation, I want to try to cover this really important question of where does it make sense to do this sort of work. By this sort of work, of course, we mean potentially using beaver as a restoration agent or mimicking the activity of beaver or some mix thereof. And if we back up a moment before we get into estimating capacity to support beaver, above this sort of basic planning question is a question about our goals and objectives, which are going to vary from project to project. So why are we even here? In the context of this workshop, we spent a lot of time talking about sage grouse and why are we looking at trying to improve riparian conditions, potentially using beaver. So we're not here necessarily to restore beaver. The beaver are the tool to address impairments of degraded riparian conditions and try to improve things for the benefit of sage grouse. So there's a very important question above this, which is, why are we here? The example for the workshop of taking you all out to Birch Creek and showing you that system wasn't for sage grouse. That was for hydrology. It was to try and improve hydrology. And so we address that sort of broader objective and assess the ability of this tool, in this case beaver, to address that impairment. Once we arrive upon an answer, or at least a preliminary answer, that we think that beaver could be an appropriate tool, the next question that's really, really important in the context of planning is, what is the capacity of this system to support beaver? Could beaver actually do what we're hoping or what we're asking them of? And that's what I want to spend a little bit of time talking about here. And all that then sets you up to properly stage projects with pilots, treatments, etc., and then talk about how we site complexes, and then before we even get into the design of a complex and the structure. Okay. So if I can get back in here, one of the things to point out in just sort of addressing this question of, can this system support beaver, and if so, to what extent, is we could start with a range map. Range maps exist for pretty much all species, and one of the things to note about the sort of beaver range maps that have been published is a lot of them are wrong. So in this picture here, this dark gray background is this blob is sort of the current thought to be where beaver were present, and there's been a number of studies where beaver were assumed not to be, and actually it turns out that we found evidence of them there historically. There's been some really interesting studies from California in this regard. You also notice Nevada is a big gap. These range maps are wrong, and in terms of not necessarily providing enough detail when it comes time to making this assessment at a local system scale. And so there's other efforts, the gap analysis, but again, these just kind of put some regions and some blobs on the map, and most of you will be working on projects on an individual parcel for an individual landowner in the context of some individual watershed. And so what about in your particular stream? And the question that we're interested in is not just whether beaver could survive. What we're after is, where are the places they could build dams? And the reason we're so interested in that, it's the positive feedbacks of their ecosystem engineering activities of building these dams that we're most excited about. So yes, they can survive in a huge range of conditions that might be reflected vaguely in that range, in some of those range maps, but where they build dams is a much more limited situation. So the classic example I always like to point to is we find a lot of beaver in the Grand Canyon on the Colorado River, and they're eking out just a fine existence down there. Of course, they're not damming up the Grand Canyon. And so the reason for that, something that we talked about earlier, and it's because the water depths are deep enough there to maintain underwater entrances to their lodges. And then, of course, the energy or the stream power is just way too high for them to stand any chance of building a dam, even at base flows. And so we see that this dam building activity varies dramatically according to flow regime and availability of dam building materials. And so what I want to use as an example to sort of guide our thinking, but don't think of this as you have to use this tool to answer this question. But I want to use this thing that we call BRAT, which is stands for the Beaver Restoration Assessment Tool. Again, I just want to emphasize it's the questions and the thought process here that are most important to getting you down the road of doing appropriate planning in your watershed or on the parcel of the landowners that you're working towards. However, this can be a good place to get started, and the logic you can apply on the ground with things like the WEGs that we mentioned. So what BRAT really tries to do is resolve where and to what extent within a drainage network, as shown here, beaver dams can be built and sustained. In other words, BRAT's all about how many of these things, like we saw on the first field trip, and not how many of these guys. And so, in a nutshell, what we do with BRAT, these are the inputs that we take into account. We take into account vegetation. For woody vegetation in particular in the dam building materials. We take into account an estimate of base flow stream power, an estimate of typical flood stream power. We have some logic for dealing with really, really flat sloped streams where they build less dams because one little dam can back up a half mile or something, and so density of dams goes down, versus on really, really extremely steep slopes where they tend not to build dams. And then we have also just sort of a basic drainage area size filter, because sometimes stream power isn't a good enough discriminator in really low gradient large rivers. This logic can be applied locally in these things, and all can be combined to predict what this output capacity is of beaver dams in either dams per kilometer or dams per mile. But we've also, for a number of places, including the whole state of Utah, big parts of Idaho, Washington, Oregon, and Wyoming, been able to run this with freely available national data sets. And I'll get into that in a moment. And so the real sort of impetus for this was the Utah Division of Wildlife Resources had this very progressive beaver management plan, and we wanted to help them with some more realistic expectations to guide the implementation of that plan. And so we developed BRAT, ran it for the whole state, and we created this basic decision support system within it, the backbone of which is this capacity model, which I just mentioned. What that ends up doing is on every little segment of stream, we have about 27,000 kilometers of perennial streams in the state of Utah. It's differentiating every 250 meter segment into its capacity. It's picking up areas like this one here where it says nothing because there's no vegetation resources, and it's right on a parking area and an unimproved campsite. Versus areas with more moderate capacities. Maybe it's limited by vegetation in that case, and resolving those differences. And so I'll show you a bunch of maps like this, and just so that you understand what you're looking at, the color scheme on these capacity outputs, if we look at it in dams per mile, it's red is none, going on up through to blue, which is pervasive. And so pervasive, we can have somewhere between 26 and 65 dams per mile, 16 to 40 dams per kilometer. And then we have these in between, frequent, occasional, and rare. So let's focus in where we took you in the workshop here on the Logan River watershed. Logan River watershed drains a big chunk of the Bear River Range here. It's broken into the Logan itself, the Blacksmith Fork, the Little Bear, etc. We've been down here at Utah State University, and on the first day we went up Logan Canyon and spent some time up here in Temple Fork. We've got 436 miles of streams in this system. And if we just take that BRAT model, there are more detailed explanations of what goes into the inputs in some of the publications referenced online and other presentations you can watch. But basically, the model produces this output across all the perennial streams. And so first thing to notice is that there are big chunks of, in this case, that's the Bear River, such a big system where we don't expect to see them building dams along the river, although they do exist along the river, just mainly with bank lodges. Up the Logan Canyon, we see this mix of pretty rare dams that we'll see every so often, pretty low, and then there's a few pockets where there's bigger valley bottoms, bigger riparian area, where we see increased capacity. Then when we get up into tributaries like Spawn Creek, we start seeing more. If you take all those segments and add them up, you've got a capacity in this system, and we think this is a conservative estimate of capacity, with existing conditions, even in their somewhat degraded state, of 7,400 dams. These little stars represent a few years ago a complete census of all the beaver dams that we did, and there's about 1,300 dams found here. So the existing capacity is about 7,400. That translates to a current capacity of about 16 dams per mile. And right now, with 13, we're only realizing about 3 dams per mile on average. So this is about 18% of its existing capacity. Now that is actually relatively high in terms of utilization compared to a lot of other places, and this is because most of this area is Forest Service and Utah Division of Wildlife Resources land, where beaver haven't necessarily been proactively encouraged, although that's starting to change, but they haven't been discouraged to the extent they have in other places, and it also happens to be pretty decent habitat. Now we can contrast that with historic estimates, and if we run this where the vegetation that drives this model is a historic historic estimate of vegetation. In our case, we've used the Landfire BPS products to do this. What we can see, just flipping back and forth between these two, is a pretty big difference in capacity. And so historic capacity jumps up to 11,000 dams roughly, and sort of a capacity of somewhere around 25 dams per mile. It should put it firmly in the frequent. And currently, only 12% of this historic capacity is utilized with dams. And so there they are side by side. And where you see the biggest losses is quite interesting. We do see quite a diminished capacity in big parts of the valley where we've heavily modified these rivers down in the valley bottoms with our land use, primarily a mix of urban development and agriculture. And then up the canyon here, you're seeing some diminished capacity under existing conditions in a few places, really where the impact of the highway and the road through there. But overall, a lot of the sort of capacity in some of the headwaters is pretty close. Places where it's diminished a little bit probably can be attributed pretty reliably to our grazing practices. And so if we take a closer look at those outputs, there's a variety of things that we get out of here. But a current average of about 1.8 dams per kilometer and a current capacity about 10.1 dams per kilometer. We can compare those, of course, with existing things. So if we look in this little watershed that we went to, Temple Fork has a current capacity, not counting some of those cool little tributaries that we were looking at, of about 111 dams and a historic capacity of 186. And so this is a pretty nice way of sort of summarizing what we're looking at here. We've done some validation work at various places throughout the state. We've done this based on it's about 3,000 dams, and in a variety of different physiographic settings. And one of the things that we see is if you start comparing the predicted number of dams to the actual counts, so there's existing and historic over here. And if we look at the electivity index, anything with an electivity index above 1, shown on this vertical axis, indicates that we have a high degree of selection for that habitat type. Something around 1 means that that beaver are neither choosing or avoiding; they're just sort of using. And anything less than suggests avoidance. And so what's very encouraging is this sort of stair step that we see in these watersheds, where the pervasive and classes are always showing high electivity indexes. Frequent, basically they're utilizing what's there, and then the occasional and rare, we do see some avoidance. A more anecdotal but focused example of that validation is, we can go up to Spawn Creek, and if we look in Temple Fork, and if we look at this, what's encouraging is nowhere where we predicting none did we find none historic before. We had low densities like along here in the occasional zones where riparian vegetation is somewhat limiting. And then in some of the places where we have the biggest stable dam complexes, so each of the stars represent beaver dams, and then these represent, in this segment from here to here, there's 18 dams over what's only a half-kilometer stretch, so very high dam densities. These stable long-term dams are indeed in the places where the model predicts frequent and pervasive. And so what's happening is the capacity sets a nice upper limit of prediction on what to expect. Up here, we went to this big dam complex up here where there was a dozen new dams that were built pretty much overnight in 2011. And what was neat is the model, even before the dams were built up there, was predicting this high capacity. And when dams blew out down here and beaver moved upstream, that's indeed what we saw. So you can take this sort of analysis. You can look across, different landscapes and get a sense about what it is. And if you want, you can make estimates of what it might have been historically, just to sort of contextualize what's been lost. So, for example, if we did that throughout the state of Utah, we would estimate that today, on the 27,000 kilometers of stream that we find that are perennial, you could fit about 225,000 dams, whereas historically, with slightly better riparian conditions, we think we could have supported closer to 320,000. You could play various number games. Don't take these too seriously, but if you do the sort of standard thing about what sort of densities of dams we've seen associated with different capacities and extrapolate those out, right now we would estimate that there's maybe something around 20,000 dams in the state, maybe as many as 40,000. And if you use some, estimates of the average high and low combinations of these numbers, you could estimate how many colonies that was, and come up with some very crude numbers on population estimates. We know that the average take in Utah right now is somewhere between 3 and 4,500 pelts from at least reported legal harvest of beaver furs. So, maybe this gives us some numbers that you can play with, and even some historic estimates that you might be able to look at. More information on this is on the BRAT website, brat.joe.org, and in this publication that Wally led that is out in geomorphology. And then finally, sorry about the resolution here, but just to point out that this WEG that Casey put together for the NRCS, really what it's doing is applying this same sort of logic. And so what you could do in going to a particular site is apply, if I go back here to the logic, if you just bear with me for a second, that's wrapped up in the inputs of BRAT. We'll get there. Oops, here we go. That's what I wanted. You could go to a place and ask about what's the vegetation present. We did this exercise out in the field. And is that vegetation the sort of stuff that beaver really like to build dams with? The things that are going to score you really high if you've got abundant aspen, willow, cottonwood, etc. Things that are more intermediate or lower is when those things become mixed, or if they're really low, if they're dominated by things like conifers, sagebrush, etc. But as we saw, they will still build with sagebrush. The things that push you to none are, when it's all bare, developed, etc. Okay, and so you could then ask that question of what about can beaver build a dam at base flow? And the answers are they can build a dam, they probably can build a dam, or they can't build a dam. And then you could ask the question, can they are those dams that they build likely withstand typical floods? And so the answers, could be yes, the dam's almost certainly going to persist. It might occasionally breach, it might occasionally blow out, or it's almost certainly going to blow out with the typical floods an area receives. And those are the primary inputs that then get combined to then make an estimate of capacity. And again, like I mentioned, if you look in the paper, you can get a more detailed understanding of that. But what we really just wanted to highlight is that the WEG is available to you now to try and implement that logic. But in a decision support context, capacity models alone may not be enough. In some places, we absolutely know they're a nuisance. And so you can basically ask some of these risk questions, the risk that beaver may pose to infrastructure, etc. We've done that using just some simple GIS layer and some very conservative avoidance sort of logic. But basically, anytime I'm too close to roads, culverts, bridges, canals, railroads, we increase the probability of conflict, and when I'm well away from those, then it gets lower. And what you can see is, for the Logan example, there's a huge degree of a high probability of conflict when we run this in this very conservative way. The real reason for that is almost every single one of these streams has a road running up next to it. We've since revised this logic to just whether or not the road is actually in the valley bottom and would be flooded, and it creates a more realistic picture. And you could also further revise that based off of, well, how reasonable, or maybe I should say how accommodating is the road crew or the Department of Transportation to these things? Are they happy to mitigate them and allow beaver to persist versus they're going to fight a battle with it? All the same, if we combine that with our capacity estimates, we can break these systems out into management zones where there's potential for restoration, where there's potential conflicts, and where habitat's limiting. And the management zones we use, and these are elaborated in some of the reports, are areas in restoration that discriminate low-hanging fruit or restoration stroke conservation zones from quick return zones from long-term possibility. What we mean by low-hanging fruit are these are areas where you've got high capacity to support beaver existing, and all you need to do is either get beaver in there, or if you have beaver already, just promote and conserve them. Versus quick return restoration zones where maybe you need to do something like use BDAs to try to improve the riparian, or sort of get beaver back into a system to increase its capacity a little bit above what it is. And it uses the historic capacity as a sort of indicator to assess how likely that is, versus long-term possibility zones where the capacity right now is extremely low, but was there historically. And with all of these, there's sort of a lens of low conflict potential. That's in contrast to these living with beaver zones, where you have living with beaver zones which have high probability of conflict and have high capacity, and these are potentially really good source zones to get nuisance beaver to translocate. And so we see a bunch of these blues down in the valleys, yellow where there's lower capacity but still high conflict potential, a lot of those along some of these roads. And then we have areas where beaver habitat is habitat limiting, either because it naturally has always been some of these little spots up in the mountains where it's just too steep, versus some of these areas down in the bigger, rivers like the Bear River here, where there's just it's too big of a river to support dam building. And we separate those from orange, where there was historically capacity, but for whatever reason our current conditions are such that we've degraded that. So this is helpful for just getting some basic management zones. Again, the model spits out something based off of the quality of the input data that you give it, but the logic is also very, very helpful to apply in a planning context. So one of the really big questions that we face in the West is, what about declining snowpack, and could we get enough beaver dams back on a landscape to maybe mitigate for this? We think that this is one of the areas where we're most inadequately prepared on the science side of things to directly answer this pretty straightforward question. If we assume that everything scales up from what we know about hydrologic impacts at a local scale and scales up meaningfully across a watershed, then maybe we could mitigate our true reservoirs, the snowpack and what we're losing there, with some beaver dams. But we do think that more needs to be done to look at this in a serious way. But just to give you some context, here's the Logan River watershed in brown. This is a projection from Klaus et al. Of basically the percent of snow historically, percent snow, so this is percent of precipitation that historically or now it's changing, but fell as snow. So 90 to 100% of our precipitation in this region has typically been in the form of snow, and this is a projection from 2035 to 2065 based off of a mean of some of the various climate change forecasts of what we will lose. And so you take an area like the Logan, and huge chunks of it are going to drop from 90 to 100% as snow down to 25 to 50% and even less. And so this has real implications for the ability of these systems to maintain resilience to through droughts, to fires, and hold on to that water later into the season. And so one of the games that you can play is, well, what if we take that really conservative model we had of capacity, of conflict potential, and we basically take the management layers that just highlighted the potential restoration zones. What we are left with is 180 miles with very low conflict potential of the original 436. And in that area, there are 664 of those roughly 1,100 dams I mentioned. And so that's telling us that there's an additional 4,200 dams that could be realized. There's only 15% of this capacity that's actually realized right now. So in precisely these areas, with low conflict potential and restoration potential, we could fit a lot more beaver dams. These also happen to be precisely the areas that are really facing threats from a diminished snowpack. And of course, if you want to ask the question, well, where would we get all the beaver to support that? Fortunately, there's plenty of places where they are still getting themselves into a bit of trouble, and could be potential source zones. So some other games that you can play if you want to clip rat down for the state of Utah, for example, just to the current sage grouse range, you go from 27,000 kilometers of stream shown here, covering 47 or intersecting 4,700 square kilometers of valley bottom, and you'd just drop that down. You'd be dealing with about 96% of what's possible if we just clip it down to the current sage grouse range. Now, if we clip it further down to that more realistic estimate of where are the priority conservation areas for sage grouse, we're going from 26,000 kilometers of stream down to 2,900 kilometers of stream and about 600 square kilometers of valley bottom. So shown here where you still have colored streams left. So we see this big area up in the Raft River Range in western Box Elder County, big portions of Rich County here in the Bear River Range, various areas off the edge of the Wasatch Plateau, Boulder Mountain, etc. to the south. Now, if we clip that to the area where NRCS does its business, basically instead of just those priority conservation areas that are also on private land, now we're going from 4,800 kilometers of stream down to about 3,000 kilometers of stream, 600 square kilometers of valley bottom. You want to talk about directing your cannons at places where you could affect change. This is a reasonable place to start. So within just that, we think that there's a current capacity about 25,000 dams that you could fit in these areas. Now, we wouldn't ever expect to see 25,000 dams at once actively maintained, but under ideal circumstances, you could expect something like 40 to 50%, and in individual reaches and little subwatersheds, you could expect those to be much closer to their full capacities, and hopefully providing a tremendous amount of benefit hydrologically and in terms of creating these mesic habitats and high quality riparian areas to support sage grouse and a whole host of other flora and fauna. So to take away from this, the heart of BRAT's a capacity model that predicts the upper limit of dams that the landscape can support. The model can be run with nationally available data sets, and we've done that for a number of places. You can also implement it with higher resolution outputs or inputs if you have them, or just take the logic and then implement it in the field. And I think from a planning perspective for individual projects, you can use the nationally available data and the initial runs to just kind of get you in the ballpark, give you a rough sense as to what to expect and how that compares with neighboring areas, and to contextualize things for stuff like funding proposals, etc. But then when it comes down to the local implementation of this, you want to take those predictions and go out and take a more refined look and use that to get an idea of what could be achieved locally. It also can highlight in areas that have low capacity currently what might be done, especially when you combine this with things like the riparian condition assessment that we looked at. What could be done through changing up and improving the sort of grazing management, for example, or in a lot of cases, what might be limiting has nothing to do with livestock grazing and everything to do with wildlife management, for example, elk, and come up with some better expectations. Finally, it is just a model, so don't let this be a substitute for thinking. This relatively simple model performs surprisingly well across a pretty huge range of circumstances, but it's just there to help ask the right questions and to help develop some realistic expectations. So don't just because there's a color on the line on your little segment, you don't need to take that as gospel. You can kind of look at, well, were the inputs correct? Am I getting the right answer for the right reasons? Or if I'm getting the wrong answer, am I getting them for the right reasons? I.e., the inputs were from satellite imagery and it was out of date, or it was poor quality, etc. So that's all I wanted to cover there. Do feel free to get in touch if you have any questions about that. But I hope that helps you guys in terms of planning some realistic projects. Okay.